Hiram to the evaluation goals. Joint work with the
Yes. Okay. So hello everyone. Thank you all for being here. So the idea for today is to speak. I'm going to speak about the dual of codes or evaluation codes. And if you are familiar with algebra geometry codes or codes that use commutative algebra, this is going to be maybe trivial for you. If you are not familiar, well, my goal is that you see, well, maybe the AG codes are not as difficult as I thought, or maybe I can use them for something. Okay. So this is a young world with many great people, and I'm going to try to say who is around. And well, classical two definitions, we have just to set up the notation. Well, we are going to use classical coding theory with Hamming distance. I know that there are people who are working with many distances now. We are going to focus only on Hamming distance. And we are going to use the dual respect the classical inner product that you learned when you were kindergarten, maybe. So it's the classical inner product, okay? The Euclidean one, no Hermitian, no Galois, just Euclidean inner product, okay? And again, my goal is that you see that, show you that representation matters, okay? And the way in how the algebra geometry codes are defined, well, you have some curves and you have some Riemann-Roch spaces and you need to find some solutions of certain equations. Well, all this true, but maybe they can be seen a different way, okay? And this is what I want to show. And remember, the representation matters. And why do we want to study the dual of the code? Well, for me, the dual is one of the most important objects in coding theory. Sometimes they have the same information of the code, and sometimes the dual is easier than the code itself. Sometimes the information is complementary, and you can use one to deduce the other one, right? So we know the MDS, and also McWilliams identity says, well, if you find the weight distribution of one code, well, you can find the weight distribution of the dual. So this is complementary in some sense. And if you are not familiar with the permutation group, well, thanks to the permutation group of the Reed-Muller codes, they achieve the capacity, right? So it's because they have the affine group inside of the permutation group. Well, it's exactly the same. And if you are not familiar with the permutation group, so the question is, I have this code, very simple. And the question is, so which columns can I permute in such a way that I still have the same code? Okay, so the code, remember, is a row space. So which columns can I permute? Well, I have no idea. But the point is that the permutation group is preserved for the dual. So in other words, the dual and the code, they both have the same permutation group. Okay, so I'm going to ask you this, and you can say, well, the dual is that guy. And you can say, oh, maybe I know the answer because I know which permutations I can apply here. So this is another reason why we want to study the dual. And what else can we do? Well, these are just classical objects in this sense. Well, the MDS, McWilliams, we all know this theory. And the permutation group, well, we also know that this can be preserved. But more things can be said thanks to the dual. Now, let's imagine that this is a code word in a Reed-Solomon code. Okay, Reed-Solomon code, length n, dimension 5, and we lost one entry. I was walking and I don't know where I left the entry. And the question is, how can I recover that entry? Well, it's a Reed-Solomon code. It's just interpolation. And I just need to know the value of 5 entries. And that's it, right? And imagine that, so we have here a certain extension, right? So imagine that we have an extension 8. So in other words, imagine that every entry represents bytes. Okay, so what this problem is saying, well, if you lost one entry, you need to download 5 bytes. Okay, can I improve this? Well, the answer is yes, thanks to Mary. Mary, thank you. Mary and Bankat, they said, well, yes, you can do it better than downloading 5 bytes. And what you can do is you can download a small piece from every code, from every entry. So instead of downloading 1 byte from these 5 entries, you can download 1 bit from every entry. You need to access more entries, but you just need to download 1 bit. Okay, so in total, here you need to download 8 times 5, 40 bits. Or here, you just need to download 9 bits. Okay, so they are different, and so sometimes it's better to download less. Okay, and why is it possible to do this? Well, it's just because this polynomial here that depends on the trace, which is a polynomial of degree q to the t minus 1, represents a code word in the dual of the code. Okay, so thank you. Thanks that we know what is the dual of a Reed-Solomon code, and this element belongs to the dual, we can play this game. Okay, and that's it. So the knowledge of the dual help us to say theoretical things about the code, or help us to do some nice applications. Okay, and then remember, the representation matters. So this is the goal of the talk. And I want to explain about the dual for some codes, and about the representation. And what is an evaluation code? Well, the definition is very simple. You take some points, whatever you want. They can be on a certain extension. They can be on several variables. It doesn't matter. So in this very simple example, I am taking points on the plane. You can take points in any number of variables, any number of entries. And you are going to take some polynomials. If you are using points in an extension, well, you need a polynomial in one variable. If you are using points in 2, 3 dimensions, you need polynomials in 2, 3 variables. Now, of course, you need to plug in the points into the polynomials. And now, for every polynomial that you take here, you are going to plug in the points, and you are going to get your code word. Okay? And in general, the evaluation code depends on 2 things: the points that you are using and the polynomials that you are using, or the functions. And that's it. And now, so usually we always say that the minimum distance is more difficult to find than the length and the dimension. And I like to think about this. And if you take a look, the length of the code depends only on the points that you are choosing, right? This is not always trivial. If you are using solutions of certain curves, when you need to find the number of solutions, it doesn't matter. The point is that the length depends on the points. Now, the dimension depends essentially on the polynomials that you are choosing. So the length depends on the points. The dimension depends on the functions. And what about the minimum distance? Well, if you want to find the minimum distance for this kind of codes, you need to find the function that has the maximum number of roots. That's it. So the function here that has the maximum number of roots here, that is a minimum distance. So for the minimum distance, you need to know very well the 2 objects, okay? And it's true that the dimension depends also on the points, because you cannot, you want an injective function, but well, in general, we say that the minimum distance is more difficult because you need to know how are playing the 2 objects. And now you are thinking, oh, I'm not again algebra geometric codes. I don't like algebra geometric codes because they are using certain fields, and I want to study binary. Well, any code can be seen as evaluation code, okay? Any code. So my goal of this is that you can see, maybe you can play around with the polynomials, and you can see your favorite code. You have an LDPC code, which means that you have a sparse matrix. If you have a sparse matrix and you find the evaluation representation for the sparse matrix, you have polynomials of higher degrees, right? Because you have a bunch of zeros. So if you have a matrix and you have no idea if there exists a sparse representation for that matrix, find the polynomials that represent every code word. And if you have only low degree polynomials, you cannot find a sparse representation for the matrix. Okay, so what I want to say, well, any code is an evaluation code. And how can we see this? Well, let's say that we have the code. We have a certain code over fq and length n. It may happen that n, as usual, is larger than q. It doesn't matter. So take m in such a way that now n is less than the power of that number, q to the m. Okay? And now take n different points, the points that you like, the points that you prefer. It doesn't matter. So you can take the points in n variables, like here, or you can take points in this field extension. It's okay. So you will have polynomials in several variables, so you will have polynomials in one variable. But the point is that you want to see the code as an evaluation code. And what is the next step? Well, I have the points, and now I need to find the functions. For every point, there exists what is called indicator polynomial, or is also known as separator polynomial. And what is the meaning of that? Well, you can use Lagrange, and it's a polynomial that has the property that when you plug in this point, you get 1, and when you plug in the rest of the points, you get 0. Okay, so it's a delta polynomial. Those polynomials always exist for these kind of things. So now you choose your points, you find the indicator polynomials. Now for every code word that you have in the code, well, you can define this polynomial, which is the linear combination of these indicator functions, which are these CIs are coming from the code word that you want to represent as an evaluation, right? And of course, when you evaluate these functions on all those points, because you have linear combination of indicator functions, you are going to have the code word that you want. And now you say, oh yes, but it's for every code word in the code. Of course not. You just need to take a generator matrix. You have k rows, and for every row, you find one polynomial, and you have your evaluation code. Okay? So now, you remember, you can take your favorite code word, your favorite code, and you can see it as an evaluation code. Okay. And why do we want to study this way? Well, because the representation matters. It depends on what you are doing. So maybe you cannot solve the problem, and seeing this way, you are going to be able to do it. There are some bounds. In general, you can find the representation, and the highest power that you find in the polynomials, that is a natural bound for the minimum distance, right? It's called the footprint bound. So you have a bound that is not coming from the linear code if you don't have the evaluation representation, okay? Representation matters. And for instance, Professor Calderman and friends gave the definition for CCST code. The CCST codes are important for some quantum codes with certain T gates. It doesn't matter. The point is that if you want to find this kind of quantum codes, what you need to have a pair of codes over F2 to the n that satisfy these properties, these two properties. If you know the definition, well, it's great. If you don't know, after 5 minutes, you will understand the definition. It depends, the code should be even, and then for every code word there exists a self-dual code inside with a certain support. You can do it. But I told you that representation matters. And even if you understand this definition, if you want to find this pair, let's say you have a computer and you want to find a pair of codes, I don't know if you see here, but for every code word, there exists something. And when it says for every code word, I cannot do it because, it's going to be computationally hard. But the representation matters. It turns out that the same definition that you see there about CCST pairs can be written in just this very simple thing. Okay? So all what is written here, C2 inside of C1 reduces to and on this thing. And now you can find pairs of codes. So the representation matters, okay? And if you want to find a CCST pair using this definition, and the computer, I don't know how you can do it, but here it's very simple. You take one code C1, and then you can find, this is the square, respect the component-wise product, the component by component. That is what I mean by a square. So you take your favorite C1 code, you can find the square, easy. You can find the dual, the intersection, and everything inside will give you a pair of CCST codes, okay? So the representation matters, and I don't want that give you a bad impression. So we didn't prove this using evaluation codes. So the proofs are very simple, but what I wanted to put here is because, well, representation matters, okay? And then what else we have? Well, I told you that any code, you can find a certain functions, you can choose your favorite points, and you can find an evaluation code. Well, and in this paper, what we did is, well, if you have a code, an evaluation code, how can you find the dual? Well, what this theorem says is that you need to use the same points. And here is the relation of the function that you need to use. This is the column ideal. And this guy here, if you are familiar with ideals, this represents the footprint of the ideal. You fix an order, you find the Grosvenor basis, and the monomials that are not leading monomials. That is the footprint. Or it's also known as the standard monomials. Okay? And well, the point is that there is an algebraic description. And again, you can say, well, you are not making my life easier with that. And I want to give you some implications of this theorem. Okay, I wanted to tell you how you can use it to find duals of known codes and some generalizations of those codes. We have two classical examples. We have the Reed-Solomon codes and we have the Reed-Muller codes. Now, every time that I think about a code, I have in my mind two pictures. One is for the points and the evaluation points, and another one is for the functions that we evaluate. In this case, we have only monomial codes, which means that the functions are, a basis for the functions are monomials. It's a set of monomials. And this integer represents the powers of the monomials. So this is the monomial 1, x squared, x to the k minus 1. And these are only some points in the final field. There is a classical Reed-Solomon code. For a Reed-Muller, well, here we have an example for two variables. We use all the points. And we use monomials up to a certain degree. Remember, this is the monomial 1, x, y, xy, x squared, and so far. Okay? So we have these two pictures. And, well, for Reed-Solomon codes, I think that the original Reed-Solomon code was given when the set of points was fq star. And then they had the extended, which included 0, and then the double extended, which include infinity. And now, of course, you can also take a subset of points, right? So now, this is what I mean by a Reed-Solomon code. It's just an arbitrary subset of points. So it's easy to generalize. Those are called generalized Reed-Solomon codes when you multiply by certain constants. But it's easy to generalize this family of Reed-Solomon codes. And what about Reed-Muller codes? How can we generalize Reed-Muller codes? We always use polynomials of a certain degree, and we always use all the points here. Can we do something a little bit more general than this? And yes, and what we have here is called Cartesian code on the top. We are using, again, monomials up to a certain degree. And here, we are using a Cartesian set of points. Of course, when you take fq squared, that is a Cartesian set of points. So this is a little bit more general, okay? And they are called Cartesian codes. And also, so this is the case when we have polynomials up to a certain degree, but also you can bound every variable up to a certain degree. And when you bound every variable, x, y, z, you are going to get this kind of shapes, okay? So you can take this kind of shapes, and now you can take a Cartesian set of points. And by the way, so this is also a tensor product of Reed-Solomon codes. So when you are, if you want to work with tensor products, they will have this shape. These are the monomials that you use. This is one component of the tensor product. This is the other component. This is the set of points that you use for your tensor product, and this is the other set of points. Okay? And, well, the question is, how can I find the dual for this kind of objects? And you know how to find the dual of the Reed-Solomon code, and I want that you see some properties of it. And we are going to try to use those properties to find the duals of the other families. So let's take some points, those points for the Reed-Solomon code. And now we have monomials up to a certain degree. Okay? You know that. And for the dual, well, for the dual, I'm going to use the same set of points to evaluate. And what about the monomials? Well, I am going to use monomials up to degree 1. And why? Where are these guys coming from? Where we have here these 2 points? Well, there is a very simple explanation. You can take your points. Now you put all the points together and you create a box. The box has size 5. You put on the top of these monomials that you use to evaluate, and the complement, these 2 guys, there is a reason why we have these 2 guys here. Okay? But we are not using all the points, which means that we have the dual is a generalized Reed-Solomon code. And well, we have a certain coefficients here. And well, this is just the evaluation of polynomials up to degree 1. Where are these guys coming from? Well, I told you about the indicator functions. The indicator polynomials, those polynomials that have the property that when you plug in this point, you get 1. When you plug in the rest of the points, you get 0, right? Well, you can find indicator functions for those 5 points. And when you do that, the indicator function for this point is given by 5x to the 4th plus something else. I don't care now, this something else. You can find the indicator function for the element 2, and it has the shape of 4x to the 4th plus something else. And now you can imagine the leading coefficients of the rest of the indicator functions, right? Well, what we have here is the leading coefficients of the points of the indicator functions. Those are the guys that appear here on the dual. So what I'm saying is that the dual for an evaluation code of this shape is given when you take the box and you put here, and the coefficients are given by the leading coefficients of the indicator functions. So the points play an important game.
What do you mean by the box? Like the box is an enclosing box, or?
No, it's just maybe way to say it. So you have 5 points and you shrink the points and you have a little box of size.
Just the number of points.
Yes, the number of points. That's it. Thank you. And well, this game can be extended. Remember, this is a monomial evaluation code because it's generated by monomials. And when can you do it? Well, you need to have certain properties on the set of monomials and also on the set of indicator functions. For this example, and for every Reed-Solomon code, it's going to be true that the indicator functions have all the same degree. But if you take points on the plane, on the space, or more variables, they will not have always the same leading monomial. Okay, so if you have these properties, you can generalize the same idea. And this is what I have here. And I don't want to use this. I don't know why it's there. The point is, this game can be generalized about the duals of monomial evaluation codes. As long as the code and the dual have the right dimensions, and when you multiply them, you don't get the highest power that appear on the indicator functions. This is how you can find the dual. And you can write something more general for Cartesian codes. You can have polynomials up to a certain degree, but actually you can have any set of monomials that is close under divisibility. And when you do that, the game is going to be true. And this is important because the polar codes are decreasing Cartesian codes, some polar codes. And well, let's play the game. So to make sure that is clear, we have the Reed-Muller codes. And I have polynomials up to a certain degree. And I have all the points. So now the theorem says that we can replicate the game that I told you before. Okay? So I want to find the dual. I am going to use the same points. Using those points, you create your box. You put the box on the top. And the complement, that is what you require for the dual of the code. Okay? If you rotate this and put here, it's going to be the precise size. Can we do the same for other codes? I hope so. The Cartesian. And we have a polynomial set to a certain degree, and we have a Cartesian set. And I want to find the dual. Can you imagine what is going to be the dual? Well, for the points, we require the same points. Now, this set of points is nice. When you find the standard monomials, they create the box. So the box is coming actually from the standard monomials. But well, in any case, you choose the points, and you are going to have a certain box. You put the box there, and the little complement that is missing, that is the one that you require to find the dual of the codes. And well, you don't have all the points. In a similar case than Reed-Solomon codes, you need to multiply by certain constants, something like generalized. It doesn't matter. They are coming from the indicator functions of those points. So you really know what is the dual for this family of codes. And yesterday we had a very nice talk about Hermitian codes, right? And for the Hermitian code, you heard some weird words like function fields, Riemann-Roch spaces. You can forget about it. At least for the Hermitian codes and something a little bit more general that is called norm trace code. There is another, this game that I told you, you can play it here. You can define the code and you can find the dual, very simple. And well, in this theorem, we had to find the Gromner basis. The Gromner basis is nice. We respect a certain order. The footprint is going to be, again, like a box, a rectangle, so you can play the game. We also found the indicator functions because when you need to multiply to find the dual by a certain coefficients. Here we have an example. And this is a Hermitian code. For the Hermitian code, you have a certain equation, and the points that you are going to use are the solutions for that equation. Okay? So here I have the points. And now, what about the monomials? Which monomials can I use? Well, I can use monomials in this little box. And I imagine that you know why this little box, right? Is what I just told you. So you have all these points. When you shrink the points, you are going to have a box that has size 9 and size and height 3. So that is why we have this guy here. And I'm sure that you can find the dual. It doesn't matter that you don't know Hermitian codes. You can find the monomials that define the dual of these kind of things, right? You put the box and the complement, those are the monomials that you require to find the dual. Okay? And now, you need to multiply by certain constants, but it doesn't matter now. So you have a very nice description for the two things. The Macalise crypto system is important because, well, it cannot be broken yet using the GOPA codes, right? And that is the description of the GOPA code. I remember the first time that I saw this, and I said, I don't care. I don't know what is the meaning of that. Well, it turns out that there is a very nice description for this thing. And you are using points. This is a set of points. These are the evaluation points. And these guys live in FQ to the T in some extension. And here you use polynomials that have coefficients on that extension. And then when you define the code is only on the base field. So this is a subfield subcode because you have polynomials and points in one extension, but you care only on the elements when you get elements on the base field. And I don't have the picture here, but this guy, when you find, is just the subfield subcode of the dual of a generalized Reed-Solomon code, right? So in other words, there exists a Reed-Solomon code, the classical that we know, generalized Reed-Solomon code, and then you find the dual, and then the subfield subcode, and you have this representation. Can we extend it to more variables? Well, this is what we did in this work. And if you take a look, well, it's more or less the same It's more or less the same formula. So you have this very nice representation. And this representation is important because you can find a decoding algorithm, okay? Well, we are playing more or less the same game. The difference is that here we have points in fq to the t, and here we have a Cartesian set of points. Here we have a polynomial in one variable, and here we have polynomials in several variables. And then you defined more or less the same equation. And that guy is called multivariate Gopak code. I told you that this guy is the subfield subcode of the dual of a Reed-Solomon code. So how can we represent this guy? Maybe there is a better representation than this horrible formula. Well, actually, there is a very nice representation. And it turns out that this guy is the subfield subcode of the dual of the tensor product. So here you have one variable, and using this variable and this set, you can generate Reed-Solomon codes. And here you have m variables, and you have here m entries. So with every entry and every polynomial, you define one Reed-Solomon code. And then you make the tensor product of all those Reed-Solomon codes. The subfield subcode of the dual is what is known as multivariate Gopak code. How can we represent that guy? I'm sure that you can do it. We have certain points. Here, we use the same points because it's a Cartesian set. And then I want to find the dual of a tensor product. The tensor product is just a rectangle, something like this. And the blue one is coming from the points. These guys are the evaluation monomials. And you can find the dual, right? It's exactly what you expected. That guy is going to be the dual. The subfield subcode of this object, that is what is known as multivariate Gopak code. Okay? And it has a better, I don't know if it is a better representation, it depends on what you want. And I think that this good representation is good if you want to decode. But I feel, of course, here you can find certain parameters of the code, thanks to this representation. Okay? And, well, what I want that you remember is that representation matters. Let's say that we have a Reed-Muller code. We have monomials up to a certain degree. And then using that Reed-Muller code, you all know the Reed-Muller code. And someone comes and says, can you please improve this code? What I mean by improving is, can you maybe add more functions? But I don't want to change the minimum distance. I just want to have a better rate. How can we do it? How can we improve that Reed-Muller code without changing the minimum distance? I cannot use monomials up to degree 9 because I am going to change the minimum distance. Well, that representation that I told you about the dual, about that box, that is coming from what is known as footprint bound. And the footprint bound tells you, well, find the highest monomial in your set of functions. And that is a bound, a natural bound for the number of roots that you are going to have. In other words, I want to find the minimum distance for this Reed-Muller code. What can we do? Well, you take one of the monomials that belongs to the code, and you can count the number of points that you have in the lattice from this to the corner. Anyone can do it, right? So here we have 11 points times 3, 33. Okay, so you count the number of points in that lattice, and that is 33. You can do the same for every point that you have here on the diagonal. You can count the number of lattice points, and the minimum, that is the minimum distance. That is the minimum distance of the Reed-Muller code, and it's coming because of the bound that I told you. Okay, so now that I know this game, maybe I can figure out which points I can add without changing the minimum distance. So the representation matters. You have the Reed-Muller code, which is just you have a vector space. You don't know how to find the minimum distance, or let's say that you don't know which vectors you can add. where you can find the evaluation representation. And now you use the monomials, and now it's just a game. It's the same code. It's the same Ring-Muller code. And remember, I want to add monomials without changing the minimum distance. Can I add that monomial to the code? Well, if you do that, you count the number of points, and that is going to be 22. If you do that, you will change the minimum distance from 33 to 22. So that is not a good option. And what about that one? Well, the minimum distance was 33, and it's going to go down, so you cannot add that monomial. But that one is 36. So it's a combinatorial problem about which monomials you can add to the Ring-Muller code in such a way that you don't change the minimum distance. And when you do the same, you always will have this kind of shapes. Those are the monomials that you can add. You are not changing the minimum distance. And it's not an easy task to know how many monomials did you add. It's an open problem to figure out the dimension of this guy. And it's important, right? Because you are not changing the minimum distance. You are only improving the Ring-Muller code. And well, remember?
It's like the area of a hyperbola.
Yes, it's called a hyperbolic code. And you can find the integral of these kind of things, and that is going to give you an approximation. The problem for me is that it depends on the characteristic of the field. There are sometimes you don't improve at all, and sometimes they have more, sometimes they have less. So it's complicated. When the characteristic plays a game, it's going to be a mess. This is what I think. And well, for all these kind of codes that I describe, the tensor product or the Cartesian, you can play the same game as Mary and Bank had. So you can create repair schemes for those kind of codes. And when you use a Reed-Solomon code, you have some gaps on the dimension because you can use only certain dimensions on the Reed-Solomon code. But now in this case, because you have a Cartesian set, you can play with the length of the entries, and you can fill in those gaps for the dimensions. And that's it. Thank you. Okay, thank you. No questions?
Can you say please one sentence about the third bullet? So what improvement or matrix multiplication?
Oh, yes. Yes, and when you have you can decompose the matrix. You can decompose two matrices in some blocks. Let's say K1 and big1, bk2, and in such a way that when you want to multiply the matrices, what you need to do, you need to find the summation here. You need to use the same. K1. And now you can encode these two guys using polynomials. And if you take a look, well, this is just, you can think that one guy is in the code and the other one is in the dual. You want to recover this summation. Well, you can use, thanks to Bark, you can use in the dual, you can put a locally recoverable code that has a bunch of zeros. And when you recover that guy, well, you improve some parameters.
Other questions?
Oh, yes, please.
In your examples, you showed the tensor product of two Reed-Solomon codes. Can you talk about, do you have like an explicit way to take its dual?
So the question, yes.
I don't, it's a tensor product of two Reed-Solomon codes. I don't think you showed us how to take it. Oh, this one? Oh,
Yes. Right. So this is this represents the tensor product, and the dual will have this kind of, well, the complement.
Oh, this is the Reed-Solomon.
Yes. It's not a tensor product anymore.
And this works for any Cartesian. Do you need to specifically choose a point, or is it any Cartesian product will work?
Any Cartesian product is okay.
It's okay.
Yes, and you need to have a collection of points, in such a way that the footprint, the standard monomials, when you for a certain order, is a rectangle. Okay, so this for any set of points, when you find the standard monomials, they always have this kind of shapes. But if you have a rectangle, you can play this game.
So we'll get to that time. You can choose any, like you can take the Cartesian product of any two sets, and you'll always get.
The rectangle.
You'll always get.
Yes, that is true.
Other questions? Okay. Yeah.